right, good morning. Let's get started. Sorry, it took me a little time to get that set up. So today we are talking about optimization, right? And have people gotten a chance to watch the videos on optimization? Okay, so some yes, some no. So I am happy to answer a few optimizations, or at least today. I hope everybody noticed that optimization is due Monday. This is one of the harder sections. And by harder, I just mean it's story problems, and typically these problems take just a little bit more thinking than average. And so I gave you the break to work on this homework assignment. So there's no homework due today. It will be due on Monday. So today I'd say that it will be more of a push in the right direction day and not a fully solve the entire thing day. And then maybe on Monday, if there are some questions that people are like, tried this one a bunch, just couldn't get there, then I'll maybe work through an entire problem. So I would say today, if there are some problems that you're just thinking, I've tried this and I need a push in the right direction, I would be happy to do so. But if you haven't watched the example problems yet, definitely do that, because that kind of gives you the form, and I can talk about that a little bit today too. So any questions that you'd like me to maybe give you a push in the right direction on today? Yeah.
35.
35? Okay. Okay, so the optimal soda can, part A. So find the radius and height of a cylindrical soda can with a volume of 354 centimeters cubed that can minimize the surface area. Okay. So we know on 35 that we're dealing with a cylinder, right? And the cylinder, it's a can. So we have an actual, there is a top on the can and there is a bottom on the can, right? So, and that's actually pretty important, is we're not just optimizing the area around the can. We also have to have area on top and bottom of the can. So if we're trying to optimize the surface, so that's always the question that we should ask ourselves first. It's what is it actually in this problem that we're trying to make big or small, right? What is it that we're trying to optimize or find the maximum or minimum of? And so reading this problem again, it says, find the radius and height of the cylindrical soda can with a volume of something that minimizes the surface area. So it even tells us straight up, we're trying to minimize the surface area of this thing. This can, I suppose, has some height. And we could call that H. And it has some radius. We'll call that R. And we want to minimize the surface area of that can, right? And so the first thing that we need to do is say, okay, well, what's the surface area of that can? And so what is the surface area? Well, there's really kind of three pieces. Two of them are the same. There's the top, there's the bottom, and there's all the way around, correct? So let's do the easy one first. What's the surface area, or just the area of the little circle that's on top? Yeah, that's pi r squared. And then there's another one of those on the bottom. So we've got 2 pi r squared. So that's the top and the bottom, correct? What is the surface area of the outside of the cylinder? Well, if you're having a hard time visualizing that, what if I took my pair of scissors and I cut it, okay? So I cut this right down here, and then I unrolled it. If I unrolled it, it would just be a rectangle, correct? And if it was a rectangle, what's the height of this rectangle? That's just the H that I had right here. And then how far around is the top? Yeah, that's the circumference of that circle, which is 2 pi r. So this is 2 pi r. So if I wanted to know what's the area of this rectangle, then it's 2 pi r h. So I'm going to add 2 pi r h. And now I've got a formula for the surface area of the can. Is everybody with me so far? So in the way that I usually set these up, I'd call all of this my step 1. Okay, so step 1 is, what is it that you're trying to make big or small? And I answer that question in my head. I read the question, say, I'm trying to make the surface area small, right? And then I say, okay, you're trying to make the surface area small. Good. Then you need a formula for surface area. This is maybe the biggest mistake made in optimization problems, is people don't start out by figuring out what is the equation that I'm trying to maximize or minimize. So you need to start every time by saying, what is it I'm trying to make big or small? Because there's often extra information, and sometimes that can lead you astray on what it is that you're trying to do. So I'm trying to make the surface area small. What's an equation for surface area? Okay, I have it. Now what? Well, now I'm kind of like, okay, is there extra information in this problem that will help me to maybe turn this side into just one variable? Because you notice here I have an R and I have an H. And so now I want to ask the question, well, is there any other information given to me in this problem? And there is. What is it? Yeah, the volume of the can, right? They say that the volume is 354. Okay, so I have that the volume is 354. And what is the volume of this cylinder? Yeah, it's the area of a circle stretched across h. So it's pi r squared h. So this is pi r squared h. So that's just the volume of the cylinder is 354. Now, what I can do is I can use this to solve for one of the variables up here, either r or h, and then replace the variable up here with the rest. So I think the easiest thing here to solve for is h. So I will, and I get that h would be equal to 354 divided by pi r squared. Now what I want to do is use this information to simplify my original formula. So this is h. So I'm going to take that h and plug it in here for h. And then I get that surface area is equal to 2 pi r squared plus 2 pi r times h. But h now I know is 354 divided by pi r squared. So now I have a new formula for surface area. Notice something. At the end of step 1, I have a formula for the thing I'm trying to make big or small, surface area. At the end of step 2, I have a formula for the thing I'm trying to make big or small, surface area, right? So you should never be like, oh, at the end of step 2, what I came out with was volume. It's like, who cares about volume? I mean, it's helpful, right? Because it helped us to make our equation that we're trying to maximize or minimize better, but we have to continually focus on the right equation. And that's where you can make mistakes in optimization, is we're not focusing on the right equation. Okay, so now that we're here, we could simplify this a little bit. So we get surface area is equal to 2 pi r squared, 2 pi r squared plus, okay, so we've got a pi on top and a pi on bottom here, so those pi's cancel. One of the r's cancels, so I've got an r on top and r on the bottom. And so what's left over? 708 on top, and on bottom r. Okay, so this is very good because now I have surface area in one variable. Okay, it's just the only variable I'm dealing with is r. And now I'm sort of almost ready to do some calculus. The only thing that's left to do is say, are there boundary conditions on r? Like, is there a biggest that r can be or a smallest that r can be? A lot of times the answer is not really, other than 0. But sometimes there are, because like, you know, some of these problems, like you're building a fence on the side of a barn. So you can't like go further than the barn. This one, you have to think, is there what's the smallest that r could be? I suppose r could be 0, but not really, right? Because if r were 0, the volume of this thing is not going to be 354. It's going to be 0. So r has to be some positive number. Now, how big could r get? Well, I suppose it could get very, very big if h got very, very small. It'd be a very silly looking can, but it's possible, right? And so there's no real boundary conditions on r that I have to worry about. So what I would say for like my third step, where I talk about what are the boundary conditions on r, I would say that r kind of lives inside of, here, I'll just say r is in 0 to infinity. Okay, so there's not like a closed interval on which r lives. And sometimes that comes up, and that's important because remember, if you're finding absolute extrema on a closed interval, then you have to test the endpoints. If I'm finding absolute extrema on a non-closed interval like this, then I just have to test the critical values. Okay, so all that really is going to come up on this one are the critical values. Okay, so now we're at a place where it's like, okay, I know the equation that I'm dealing with and need to use calculus on. I know that I'm in a case where the critical values are where this is going to happen. So if this thing is going to have a minimum, it's going to be at a critical value. So now we just need to use calculus as we have been up to this point to say, where is the critical value, and then where are the local max or mins, right? So let's do it. So on this one, I want to take a derivative. So I say, what is the derivative of, I guess, the surface area with respect to r? So we're moving into step 4. Actually do some calculus. So the derivative is, let's see, I bring down the 2 and I get 4 pi r. And then the derivative here, this is 708 r to the negative 1. So that's negative 708 r to the minus 2. So this is minus 708 over r squared. And now I want to set that equal to 0 and solve for r. So set it equal to 0, solve for r, I'll move over here, and I get that 708 divided by r squared is equal to 4 pi r. Then we cross multiply, and I get that 708 is equal to 4 pi r cubed. So I get that r cubed is equal to 708 over 4 pi. And then I need to do a little bit of math here, but we get that R equals something, right? So the cube root of 708 divided by 4 pi. And so that could be calculated. Okay, so what is the question? Whenever I get to the end here and I'm like, hey, I found a critical value. By the way, where could the absolute minimum happen? Well, we know that if it's on a closed interval, then it's either an endpoint or a critical value. On an open interval like this, where could it happen? Just at a critical value. So because there's no endpoints on this thing. So the only place where an absolute minimum could happen is at a critical value. How many critical values are there? 1. There's just 1 critical value. So this is where the minimum happens. Does that make sense to everybody? And it kind of makes sense if you think about it. If I started making cans that were super tall and little radius, so these tiny cans that like stood 1,000 feet tall and had a radius of like a centimeter, or if I had a big fat can that was that deep, both of those are going to be an extremely high waste of material to get the volume that I want, right? So somewhere in between of really tall and low radius and really big radius and really short, there's going to be like this perfect medium that will get me the volume that I want for the least surface area cost. And that's going to be at this radius. Okay, now, what did the question actually ask for? They said find the radius and the height that will get it done. So we found the radius. Okay, this is the R that we're looking for. Although this isn't very clean, we should probably plug this into a calculator and be a little more precise. But what is the height? By the way, what's the units on this? Yeah, this is centimeters. And then we need the height. How do we find it?
You just plug in R and H.
That's right. So over here, we found what H is in terms of R. So once we find R, just plug R in here and find the H. So we can now, that we found R, we can find H, and that's our answer. Because there's only 1 critical value. Now, if there was more than 1 critical value, then I need to be a little bit more careful. Or if there are endpoints. Okay, in this case, there were no endpoints on R. But if there were endpoints on R, then I need to test the endpoints and the critical value. Does that make sense to everybody? So it's kind of cool in some ways that like all optimization problems are the same. And yet they all can feel extremely different from each other in what you have to do because the original equation is different. But the process for solving optimization is the same like every time. You say, what is it I'm trying to make big or small? If you get that part right, you're like 75% of the way there. Just answering the question, what is it that I'm trying to make big or small? And in this case, it was surface area. Then I'm like, okay, then what's the equation for the surface area of the object? I found it. Then I'm like, awesome. Step 2, anything else I know here that could help me? And then I use that information to rewrite my surface area equation. I did that. Then I say, are there boundary conditions? No, not in this case. And then I just do my normal calculus that we've been doing up to this point in the chapter to solve. And that's the whole thing. Any questions on this one? Any other questions? Somebody, yeah. 48. I probably won't do the whole thing, but we can look at it. So we've got a cylinder and a sphere. Find the height H, radius R, and volume of a right circular cylinder with maximal volume that's inscribed in a sphere of radius capital R. Okay. So we have a sphere, right? And that sphere has a cylinder. I guess I'm sitting inside of it. Right, and this is a sphere. Okay, so what we know is that this sphere from here to here, that's capital R, and that's a fixed value. That's not a variable, right? Capital R could be 3, capital R could be 7, but it's just some number. And then we've got this cylinder that's sitting inside the sphere. Now, there's many equations that we could come up with here, but I want one of them in particular. And this is, in some sense, in my opinion, the hardest part of the problem is right now. And that is, what is it I'm trying to make big or small? So let's look at the problem again. What number was this?
48.
48. Find the height, radius, and volume of a right circular cylinder with the maximum volume. Maximum volume. That's the key. So what it is that I'm trying to make big or small is volume of the what? Cylinder. So I want to know what is the volume of a cylinder. So this cylinder has some radius. I could call it little r. This cylinder has some height. I could call that little h. And so once I've labeled this little r and this little h, what's the volume of that cylinder? And we just did this, right? What's the volume of a cylinder? Yeah, pi r squared h. Good. So that's a good start. We've done step 1. And step 1's the most important step, is we figured out what is it I'm trying to make big or small. I'm trying to make the volume big, correct? Very good. Okay, second question is, what's the extra information? And sometimes in these questions, the extra information is veiled. And that is, in this case, the veiling is it's inside of a sphere, right? So what does that mean, that it's inside of a sphere? Well, that means that it just can't be as big as it wants or as small as it wants. It's kind of like there's some relationship that has to be maintained, and you've got to kind of look for it. And in this case, I could draw this radius from here to here, but I could also draw this radius from here to here.
And that's because when you make a cylinder as big as you can, the corners are touching.
That's right. The edges are inscribed in that circle, so they're all touching the sphere, the edges, right? And so that means that this line from here to here, that's capital R. But now I've got a nice little triangle that's a right triangle, right? So my extra information that I'm looking for in this case is this is a little r, this is, what is this distance?
1/2 h.
Half of an h. So I've got that r, little r squared plus half of an h squared is equal to capital R squared. And it's important to remember capital R is just some number. It's not a variable. Okay, and now what we do is we look back here and we say, well, what would be the best thing to solve for? I could solve for H, I could solve for R, but ultimately, what's here? Even better, R squared. And here is R squared. And so I could just solve for the R squared and put it in here. Does that make sense? Instead of trying to solve for R, because that's going to have square roots and horrible things, And so if I can avoid it and I can just replace something here for something here, that's the best. So I could say that r squared, capital R squared, minus, if I were to square this, it would be 1/4 of an h squared. So now I could rewrite my volume formula as V equals pi r squared, but r squared is capital R squared minus 1/4 h squared times h. So pi r squared h. But now I've gotten rid of all of the variables except h. And you might say, wait, what about r capital R squared? It's just a number, right? So that might as well be 7. And now we're ready to go, so to speak. Step 3 would be what? Saying, are there boundary conditions on h? Well, what's the biggest that h could ever be? Yeah, and what is that?
2r.
2r. That's right, 2 capital R. So in step 3, so I've kind of completed step 2 here. In step 3, where I say, what are the boundary conditions? Then I would say that H is in, well, what's the smallest that H could ever be? I suppose that H could be 0. If it were, though, it would just be like a disk, like the disk that's in the equator of that sphere. So it could be 0, I suppose, although it's doubtful that that's going to be the answer. Or it could be all the way up to 2r. So H lives in there. So I suppose at some point I'll probably have to test that H could be 0 or 2r. But already I know that things aren't looking so great for that, because if H is 0, the volume is 0. And I'm trying to do what with the volume? Maximize it. Doubtful that the maximum is 0, right? But we should think about it because it is in a closed interval. So you do need to think about what about the endpoints. And sometimes on these problems, the endpoints are the answer. Yeah.
How can the height be 2r? Because like,
Yeah.
if it's straight up and down, isn't r all the way to the end of the circle?
So it would be a stupid looking cylinder, but it would look like this. So here's the sphere, and the cylinder, if the height were 2r, would just be like a line segment connecting the top and the bottom. So r would be nothing,
Okay.
but the h would be maximal.
Okay.
Does that make sense? So there could be this guy, there could be this little cylinder. There could be this cylinder. Right? Or it could get very fat and just be this disc and that's it. Right? Those are kind of the two extremes. It's like a line segment or the disc. I'm guessing both of those aren't the answer. Right? It will be somewhere in between. But it is a good habit to get into to say, but we should test it just to be sure. Especially, and I think I gave you one of these problems where you like go from a point and like swim across to the shore and then take the shore for a while. Like, and maybe there are different rates of travel along the water and along the shore, or maybe you're building a pipe across water and then on shore. I can't remember which problem I assigned, but in those problems, sometimes the boundary conditions are actually the winners. So you have to be a little bit careful about that. Okay, anyway, so that's step 3. And now 4, we do calculus, right? To figure it out. So now we have our equation that we want to take the derivative of. We could maybe simplify it a little bit to make it easier to take the derivative, but we're ready to go. And that's where I'll leave you on this one. So I think we're ready now Now you just have to take the derivative. And remember that capital R is constant.
Derivative of, or with respect to?
What are we taking the derivative with respect to? H. Because in this case, it's like there's H and there's capital R. Capital R isn't a variable. It doesn't change in this problem. So the only thing that's changing now is H. And you need to get it to that point every time. You always need to say, okay, first I just get the equation, then I get the equation in step 2 into a form where there's only one thing that's changing. And then you take the derivative. Okay. Sound good? Okay, so I think that I've done enough actually at this point to kind of give you the steps you need. And if you haven't watched the videos yet, watch the videos, because of course that's like 5 or 6 more problems that I fully work out. Any questions just about the process in general? One of the tricky parts of optimization problems, and why I'm giving you longer on them, is they're not all just the same problem. You know, sometimes you get assigned problems and I do one on the board and then I assign you 10 that are just like it, except the numbers are different, right? That's not quite like that for optimization. They all have like their little unique twist that makes them interesting. And so that's why I think that it's so important to just kind of follow the steps, is that at least the steps keep you grounded in what am I doing here? And you don't get lost in like several equations at the same time. Okay? All right. Yes, sir.
The final answer for this one, are we going to have a capital R
In the answer.
in the answer?
Yes,
Okay.
you will. So if capital R was 1, then this would just be replaced by 1. And then the 1 would sort of be in the final answer. Do you know what I mean? So, and you wouldn't notice it because it was 1. But since it's capital R, yeah, as you solve for things, the final R and H value or the volume will all be dependent on capital R. Yeah, that's right. Okay, I'm going to end there for today. So watch the videos and get started. I would say don't do all these problems the night before. That's probably not going to work out so well. These take a little time. So have a good long weekend, and I will see you on Monday. We'll talk more about optimization problems.